Hi, my name's Andrew McLaren, and I want to help you with combining vectors. This is usually used for forces in physics or even displacement, but the most useful way to do this is actually looking at components. These all three methods are going to really be breaking down one vector into its x and y components and then combining those in a couple different ways visually, but ultimately just putting all the little x's together and all the little y's together. In other words, its components all the way down. So what we're going to look at here is going to basically be just components. So when we are combining two forces or displacement or something, you can think of it as having two different x and y values that you're adding together. Now this is going to be our first vector. It's going to have some sort of change in x. I'm going to call it x1, and some sort of change in y. We're going to call that y1. And we're going to add to that a different vector that's, say, just like a little guy right here, a 2 by 3. So that's going to be our x2 and our y2. And what this could be is like maybe you're going to go on a map from one place to another and then another place again, and you're trying to figure out where ultimately you are. This could also be that there's a force pulling on it really hard one way and a slightly smaller force pulling on another way, and we're trying to figure out where's the sum of these two forces going, like what direction and how hard is that being pushed or pulled. To do that, you're going to end up combining the two. I'm going to do that in green. Now I've got a value of 1, 2, 3, 4, 5, 6, 7 here. So this was 7 long, and this is 1, 2 long. And then our y1 is going up 1, 2, 3, 4, 5. And these are positive displacements. We're just going to start real simple here. Positive 2 and positive 3. And if you do the math on that, you can see our sum of these, the sum of the change in x, is going to be 7 plus 2, which is a positive 9. And the sum of the y is going to be plus 5 and plus 3. So those get added up together to get plus 8. So if we were to think about these two triangles being put together, you can see that it is going to look, it's going up to the right, but like how much, right? So it's going over 9. So we're going to start here. 9. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're going up 8. So there's 4. There's 4 right there. And that should be our resultant vector when we put those two together. Maybe this is starting from A going to B and then up to C. There's a number of ways of thinking about this, but this is the sum of the x's and sum of the y's. The nice thing about this is that you can use this to combine more than just two vectors. But we're just going to start simple here. We're going to go with just a nice little visual overlay to go ahead and prove that this is how this is working. When you put those together using components, you're just putting together these x's and y's and adding them up. And the other two methods, you're going to see how that ends up also being the case. So the triangle method is very similar to our components method, but instead of adding up like our x1 and x2 visually like this, you can kind of see those components, how they're being put together. And then we've got our y1 and our y2 being put together with those components like that. That's pretty useful. But a lot of teachers try and do like a shortcut or a nice visual way, but people get confused what they're putting together and why. And I really get bothered by it. So if we just take our red line right here and we use that as our first vector, we're going to combine that with the second vector. And how you do that with this triangle method is you just kind of, where one ends, you put the other one. And the resultant is just where these two, and like the start and end point are. So you can kind of see how that works. Like this is a triangle, it's got three sides to it, but it's like, wait, what are the two things I'm putting together? and how does that make the ultimate big picture combination. If you look here, you can see that we're still combining x's and y's. Like there's still some sort of x component here that we are adding up the two little triangles to get. So you can see that that's still present. It's just not really drawn when we do that method. So the parallelogram method is probably my least favorite way of doing these problems, but it is still useful to go over because a lot of teachers teach it. So what you're doing is you're basically doing the triangle method, but like two of them. So you can start with your initial start point here, and you're going to have this other triangle or vector kind of go on top of it. And there's this resultant which can be formed by those two being put together in that order. Or you can take the same two vectors and put them together like so. So you can start with the blue and then add the red on top of it. This is just saying like add these components up correctly. Like you can have x1 being first or x2 being first. Doesn't really matter. You're still adding up the same components. So this piece right here is still being added to like this blue piece right here. It doesn't matter if you want to do it first or last because it's the same distance. It's just like, do you want to do the blue or the red piece first? That's effectively how you can think about this. And you've got your blue there. You got your blue here. And the red component there. Red component there. So in other words, you're saying, do I want to have like the red number first, this +7, and then the +2, and that's going to add up to 9 no matter how you add those numbers up? Or do you want to have the +7 be the second number that you're adding together to that +2? Either way, you still get the same sum of +9 when you add those up. So that's the three methods just done really quick with positive numbers. I will do negative numbers very quickly just to show this as well. So let's say we're combining this orange line with this light blue line. You can think of that as components where we are going to just break this down into x and y components. This looks like this is a positive number and a positive number. It is going over a certain amount. It looks like 1, 2, 3, 4, 5. So this is a +5, and then up 1, 2, 3, 4, 5. So we've got +5 for both of these x and y values. So I'm going to call that x1, and this is y1. Now in this case, we're going down and over a certain amount. So our y2 value here is -3, and our x1 value is -1. So you can add those up to get a resultant vector by combining these two. It looks like our sum of x's here should be 5 - 1, aka a +4. And then the sum of the y's should be going +5 right there, and -3, so it's a +2. So our resultant when we put these two together is going to be something that goes over 4 and then up 2. So that would be our resultant right there. And to prove that that really is our two being put together, we can just go ahead and do a little visual overlay of them. So we've got our first component going way past that, and then the second component kind of bringing it back a little bit. And you can see that, yes, those do work that way. So we can also do this with the triangle method, like what we did in the last problem, where we have these two smaller vectors kind of just being overlaid, and where one ends, the other one starts. We kind of showed that just a second ago with the proof. But you can see that we've got a resultant vector that goes over 4 and up 2 because we've added these up correctly. We can also do this with the parallelogram method, like what we did on the last one. Very similar, but instead of just doing one triangle, you're doing two different triangles laid on top of each other to get this resultant. And see, this is where it gets tricky and why I'm trying to do similar colors to the last one, where green is the two being put together. Because people are like, wait, what are the different parts of the triangle and how am I doing that? So we know that this plus that will get us to this green ultimately. And that's one part of this parallelogram, if you will. But this is a little bit weirder when you do it this way for this particular method, because it doesn't really look very neat. It is still a parallelogram, and you've still got these two components being put together to get the green, but it's just a little bit harder to see than when we were just working with these positive values to get from going from one corner of this parallelogram to the other corner. But it is still the same math. Like, we still have a +5 and a -1, or yeah, -1 here, and those are being put together to get you the green. So you've got the +5 and you've got the -1. When you put those together, you have a sum of +4. It is a little bit harder to see that here, but still is present. And we've got like our +5 here and our -1 right there. Same sort of deal. You can add these numbers up in different orders. You'll still get the same sum. You know, that's just a little bit of math from middle school, when you can rearrange things algebraically. It doesn't change the value of the numbers when you do addition in a slightly different order. So you can see that with our x components. I'm just doing the x's to keep it simple, but the y's also work the same way. So we've got two different problems going through how this is just combining components to get a bigger thing. So you're just adding a bunch of little numbers to get larger numbers in the x-axis as well as in the y, and then putting that together to get our 2D shape. And you could do this also with like 3 dimensions. You can also do this with more than 2 vectors. You can do this with as many vectors as you need. Maybe there's like 5 or 6 forces acting on something. You need to break them down into components, add those up, and then look at the whole picture together.